the next four presentations. So first off, I would like to invite Hadi Hajibeygi to talk about underground hydrogen storage. Please, Hadi.
Hello, good morning, everyone. It's my true pleasure to be here as a new shareholder, and also this is my first time in Canada as well. So that's also very nice. My name is Hadi Hajibeygi. I'm a colleague of Sebastian. You just heard his fantastic lecture, and I just started as a new chair. The topic that I'm going to speak today about is about underground hydrogen storage and about the framework that we have established at TU Delft around this topic. And the chair that I hold is about subsurface storage and multiscale modeling. It's not new to this audience here that we consume a lot of energy. And the scale of energy that we consume per country is in the order of several terawatt hour. Tera means 10 to the power 12. And at the same time, to support this blood to the prosperity of the societies, we as consequence also emit a lot of CO2. In the country Netherlands, we are consuming about 800 terawatt hour, producing about 150 megatons of CO2. In Canada, about 4 times of that. Population of Canada is about 38 million. So if we want to meet our target of 2050 to cut the emission to 0, it's a lot of CO2 we need to get rid of. A lot. And at the same time, we should provide a lot of energy as well. Electrification is not the only answer to decarbonization, and we all know about it. It may look a bit romantic to think that I'm driving Tesla and I'm solving climate crisis. Yeah. So that would mean that we are working on subsurface storage, which provides solutions to both sectors, energy problem or challenge, at the same time climate crisis. It provides the largest scale battery to supply the energy security in the order of terawatt hour. At the same time, it's a giant, reservoirs are giant spaces for storage of larger scale CO2 and other things that we don't want in the atmosphere or our environment. Depending on the application you are looking at, you would like the stored fluid to be inside the reservoir, no leakage to happen. If it's an energy carrier like hydrogen, you want it also to maintain pure. You don't want to lose purity while it's being stored, no matter how big the reservoir is. And also you need to operate the reservoir below the critical stress. And why would you do multiscale for it? We have a multiscale life and also geology as well. Sebastian presented an excellent example of the geology that subsurface reservoirs are multiscale in nature. So the overview of the challenges that we are looking at is about how to connect the physics of a storage that takes place in micro scale channels of porous samples and operate the system at the kilometer. And if you store it in the subsurface formations, for example, in porous reservoirs. And the level of uncertainties that we accept these days, especially if we move to hydrogen, the gold fuel, the level of uncertainties that we expect from our geoscientists is much, much less than when we had oil and gas time long ago. You would produce reservoir, it contained oil and gas. Now you want to store your hydrogen for which you have spent a lot and you don't want the uncertainty to drive your project into risks. So we need more geosciences and more technologies to develop. So as to start with this, as reservoir engineers, what we like is to prototype it with a kind of a given property of a reservoir. Let's prototype it with a reservoir model, a cartoon that you see on the right top bottom of this picture. You would populate the heterogeneities, properties, if you have fractures, if you have faults nearby. you would populate that property, and then you need to also populate fluid physics. How would hydrogen interact with reservoir brine? How about other gases? And then it comes to the challenge. This has been done in the literature as well about the feasibility study of hydrogen storage. We have also done that for the Ministry of Economic Affairs of the Netherlands as well. But the thing is that you come to populate your reservoir model. What would you use to populate properties of hydrogen? That's actually one thing that you need to have a meaningful understanding of your system before you move too fast to do dynamic simulation. And this is why we have established in Delft a hydrogen laboratory, upgraded our CO2 storage laboratory, that allows us study the process across the scale in the lab to understand what does it mean actually to work with hydrogen in the subsurface. At the same time, experiment is not enough. You need to supplement it with computational sciences to understand the theory behind it and be able to replicate or duplicate what you observe in the lab. So that's the entire program on the hydro and thermodynamics of underground hydrogen storage. Rock mechanics obviously is extremely important. And to give you an example, well, Rick is here. I saw him in the morning. I wouldn't dare to talk about geomechanics in front of him, but that's fine. Also, Giovanni gave also a fantastic talk yesterday about rock mechanics. But rock mechanics, again, we can't go too fast to the reservoir scale and system scale of multi-caverns operating for hydrogen storage. We need to understand what does it mean to cyclically load our rock material on the frequency and loads that are relevant for hydrogen storage, which is very different than gas storage. And then to understand from laboratory, how would that material behave under cyclic loading? And then develop models for plasticity and viscoplasticity, creep, etc. Understand this and then populate your dynamic simulator. The rest we know what to do, right? So that's the entire program on the mechanics of this story. And so I'm going to give you a little bit of results that we have discovered so far. The first thing that we collectively thought in Delft was, let us just start by looking at hydrogen. How could you model or understand or work with it without even having the opportunity to see it? So we took a captive bubble cell, a cylinder filled with reservoir brine, and started to inject hydrogen bubbles in it. The simplest possible scenario you could imagine. The bubble of hydrogen goes up and touches the rock. That's the rock at the top that you see. And we started to do physics 101, which is, well, we have Young-Laplace equation, fit the curve, understand the wettability. Wettability studies of this bubble dynamic told us that the system is very much water or brine wet and it's hydrogen non-wet. That was fine. And we expected it a bit as well. But now we turned off the valve of hydrogen. That's at 100 bars. We connect methane, gas in this system. Because at the end, you want to know how different hydrogen is compared to what you already know. When we injected methane, it was surprising to us. It behaved exactly like hydrogen. And we thought, oh, how can it be? How can we publish any paper about it? If it's the same, or what can I do with the grant and what? An academic crisis happened, right? And then we said, why is it that the two are exactly the same? So that's what Leila and Martier and Willemijn and others in the team did. And I agreed with them to come up with a theory behind it. And they said that when bubbles come to contact with the rock, what are the acting forces here? Capillary interfacial forces and gravity, buoyancy. The ratio of the two forces is known as bond number, NBO. For hydrogen and methane, that number is exactly the same. So they have different interfacial forces, but they have different buoyancy ratio too. That's very promising because if the bubbles come to contact with your shale rock, where it is a stationary type of trapping, the trap that was for methane would be the trap for hydrogen too. Dynamically, no, because viscous forces would be important too, and the two are very different. But when it is at rest, it would behave the same. And we were on fire when we found that the two make sense. The observation we had made sense. And we moved on. So Wilhelmine said, well, that's only bubble. What if we move it through channels of different type of sizes? So we had this microchip experiment. Wilhelmine injects hydrogen from the right and observes what are the contact angle and wettability properties of hydrogen from different perspective of different channel sizes. And you see the spectrum of from 50 micrometer all the way to 130 micrometers, the distribution of it. And some samples, experiments in the literature we found were matching with some specific channel width that we have observed. And so we could analyze that most probably those experiments were conducted for the channels that are in the range of, let's say, either 130 or 50, etc. But we found here the distribution. And then also we came up with a theory to describe why is it like that? And it would need a little bit of time, but you can discuss with Wilhelmine and Marty, they can explain to you. But we understand why, based on tighter porous samples or larger porous structures, why wettability would change slightly as well. You don't see a lot of hysteresis there as well, because they are straight channels, by the way. And now, moving on, we said, let's just take the core flood experiment. So we took a core of 17 centimeters, and that's what Marty actually did, and she's standing, sitting here. She can correct me if I explain anything wrong here. So it's 17 centimeter rock. We put it under CT and we inject hydrogen at 100 bars. And you can imagine how many of management lines I have met to get the permission of this test. So it's 100 bar hydrogen is flushed into the rock and taken out. And we do that cyclically. To understand at core scale, how does this hydrogen behave? And we get relative permeability curves, etc., that are hysteretic. We understand different processes in drainage and imbibition that I would just encourage you to discuss with Marty about it in her poster time. But that's very much interesting for us because now we can take those and put it into reservoir simulators to understand what is it that we are trying to understand. How about the computational part of the program? At the subscale, we started from molecular dynamics to come up with the understanding of when hydrogen comes into contact with brine, what are the properties, wettability properties, or diffusion dispersion properties. Extremely interestingly, we found that molecular dynamics gives you exactly the same results as you have found in the laboratory for interfacial tension. And that's the work that Wilhelmine has done, and she has a poster about it. Kinetics also gives you exactly the same predictions about mixing of hydrogen with other gases. Other gases are used as cushion gases, like nitrogen or existing methane of the reservoir. It's very important for purity assessment to know about those. But for CO2, we are thinking of CO2 as cushion gas, and then store hydrogen in the subsurface. Hydrogen and CO2, supercritical CO2, it's very complicated. We are still working on it to understand its mixing properties. And then obviously you take those and put it into porous scale solvers to understand computationally your relative permeabilities, capillary pressure curves, that then tell you that no study in the literature matches well with what we get from this physics-based approach. Yeah, and to the reservoir scale simulation now, and this is also the talk that already Sebastian covered pretty richly today morning. The level of uncertainty we accept in hydrogen or underground storage is very, very low. So we need to really understand what is the system we are working with. And so we go to the heterogeneity to take care of heterogeneity pretty well. And then we allow adding fractures in an embedded manner so that you don't change the grid size or grid topology, etc. And you can connect it with any simulator to allow it to capture these features flexibly. At this moment, we are working to adding mechanics to this because rock mechanics is extremely important for these analysis. And then we found in the field scale analysis that there are so many considerations when you work with the properties of hydrogen. Properly addressing its dispersion diffusion is very important. Hysteresis is very important. And also with the pharmacer, Susanne Herter, who is now moved recently to Netherlands, we are also working on putting all this information into into CMG framework to have a field scale in Australia to study. But I'm sure that we will get a lot of input and insight from other groups, especially Eric McKay also at Heriot-Watt is also working on this. And finally, to the rock mechanics, I just would like to tell you one story. And we said that let's go and find a gas storage site in the Netherlands. There is a site in Netherlands, it's called Berghemeer Gas Storage. And I've got already some Dutch accent, as you can imagine. And this Berghemeer Gas Storage is storing gas. And hopefully in the winter time, we are gonna use it a lot. So we get a rock specimen, we benchmark our finite element rock for the creep and plasticity. We got the experimental data from Mark Zoback and Ruben Juanes group. And in this time, we are extremely interested to working with Rick lab to get those data for the specific rocks that we have. And then we populate our field scale setting with it. The black zone here is the reservoir, by the way. So then we get to know the properties, what sandstone, what rock salt, what are the properties, and then go to the field test and look for the first 1 year and 8 months where you have enough one cycle in the pressure of the reservoir, injection and then production, and you try to tune your plasticity coefficients and then say, now go ahead with the other cycles of injection production of your gas. And our predictions match quite well with what measured data is in the field. So it means what Behnam wisely mentioned yesterday, that if you understand the physics, maybe you don't want to enrich it any further, but there must be some also cases that then physics would be very complicated. So a lot of other approaches. This is extreme, all 100% physics-based approach, what we have done, no data-based, etc. yet coming here. So with that, if you allow me conclude, today, collectively, I guess this is my certain idea that we understand the wettability of hydrogen in the subsurface. Dispersion, diffusion, mixing still remains a kind of an interesting topic. Sebastian has a project soon on this subject. And Darcy scale physics is very important to let us understand this new gas. And so to understand how can we translate what we know in oil and gas business and CCS to hydrogen now. Scaling laws are crucial to let us understand in what aspect hydrogen is different than any other gases. And dispersion is very important because we are thinking of what would be the ideal cushion gas for hydrogen. And if we can make it work with CO2, we will shoot 2 targets with 1 bullet. We store energy and also we store hydrogen, CO2 as well. So that would be ideal. And the plasticity is extremely important, and extremely important here and missing in the literature is experiments to be done in the range of stresses that we have in hydrogen and the cycles that are needed. And I did not talk about geochemistry and biogeochemistry, especially because there are so many activities that can happen that hydrogen would be consumed by bacterial activity, and then you may get unwanted gases like H2S. And so next, I hope that I'll be busy already in the group with the next few years to come and update you about this topic. So I would like to thank a lot of people, a lot of students and postdocs who helped us to get through this path, and a lot of colleagues, and very luckily now Sebastian is at Delft, so we are gonna scale up as well. So thank you very much, and I'd be delighted to take your questions.
Thank you, Hadi. Question online here from Zheng Wang. In general, how much percent of hydrogen storage can be reproduced from your storage? I guess from your storage, yes.
So I would assume that the question means if you store and reclaim it, how much recoverability is. Well, we aim for 100%. That's the wanted thing. What you wanted to say something?
Well, I was going to say there's going to be a residual saturation of hydrogen.
Yeah, absolutely. But it does not come always to contact with the brine, but also with the cushion gas. And depending if you have methane there, do you want the diffusion dispersion would be the limiting factor here, and potential also bacterial activities. In the first cycle, depending on the heterogeneity of the system that you may have, you may lose some, like 30%. So it might be, our studies would say 70%, but then through the cycles, it gets improved and then goes above. But this is just to study and analyze with no intervention of how would you do that. There are some prototype sites that are working on in the pilot test in Austria to actually store hydrogen with hydrogen as the cushion gas itself until we understand the mixing as well. And there is a company, ROG Austria, which is very much into this hydrogen storage in Europe. And they did the first demonstration in the porous rocks about 2007 or 8. And they store 20% hydrogen, 80% methane. And now they're doing 100% hydrogen. Site is being prepared for it.
So I guess my question would be as well, you've done your well perm, at least from the lab scale. If you kind of put it into a pseudo reservoir and store 100% hydrogen, and you run your simulation out as you produce it, replacing with water, whatever, what's the recovery factor, so to speak? Like in the end, how many percent? Is it strictly a residual saturation of hydrogen?
But to be honest, if I would design the system so you get it close to 100%, if I have the choice, because in my view, storage is like buying a house. Location, location, location matters. So you get the right site in the right structural trapping. So you have a cone shape. That's where you're going to operate, and that's your trap. And then you inject hydrogen. It would be somewhere around your well so that you can take it back if you want. That's what we are actually working on.
Okay.
And that would require a lot of geology also understanding.
Great. Thank you. There's a question on the floor here.
Is it working?
Yes.
Yeah, it's working. So this is Maza Irani, and I got multiple questions for you. And so for now, it's transportation and hydrogen is still an issue, and like what's been in Canada and like other places. And you also mentioned Australia, they go 80-20, and they're raising it at 30% hydrogen and 70% hydrogen. I always was thinking about, because hydrogen is enthalpy carrier and methane is also enthalpy carrier. And you got so much, in North Sea, you got so many reservoirs with the cap gas. And what's the driver they're not storing the hydrogen in those parts? Because if you're gonna use it at the end as a mix, why you not put it in some places that you already got methane or something like a gas in there and you just use it? Because there are both enthalpy carrier, hydrogen is a bit lower, but what's the driver they're not doing it? If they're planning to do it, have you guys done any solubility analysis and see what would be the difference, like a regular PVT and stuff? So that was, I was thinking about like how the bubble point would change if you have a hydrogen, because the document is very rare. You have so much data on H2S, nitrogen, and CO2 as comes methane, but there is nothing on the hydrogen. I ask you later one.
I'll try to find time for this. I mean, to remember, you asked two extremely interesting questions. The first one was about the location, and especially to know that we have infrastructure already for gas and in the North Sea area, which is in some aspect is quite populated with a lot of projects that are going on there. And we know the subsurface there also pretty well. This is ongoing. The largest European hydrogen project for a power plant is actually in the North Sea in the Dutch border side, which is called North Hydrogen. And by 2030, it is supposed to bring 10 gigawatt power for only hydrogen production. So it's only developed only for hydrogen production. And we have done techno-economics studies to see if our manufacturing companies like Tata Steel, which is big steel factory, if it wants to run on hydrogen, what would be the infrastructure for it? It is at this time that I'm speaking with you, these are on the plan. And especially because of the security of energy in Europe and not relying on the East Europe supply because of the crisis we have, the policy of the European Union is more on hydrogen-based systems. So there are going to be 10 million tons of hydrogen to be produced inside Europe and 10 million to be imported. And we are thinking about Africa as the potential sites to produce green hydrogen, transport it to Europe, because the cost would be a quarter of the cost that would cost in Europe. So, and the hydrogen here would be very attractive because of security of supply, and also because you can produce it cheaply somewhere else, not necessarily where you want. And the transportation of energy with hydrogen would be much better and much faster and economic than electricity when you think about several kilometers of scale. So that's what I could give you and the shortest snapshot about the topic you said about the first question, but this is a big discussion about what should be the energy security perspective in Europe in the coming years. The second question you asked about understanding thermodynamics of hydrogen better and the table.
With the oil, yeah.
Yeah, or solubility and all the kind of, at this moment, we are actually working exactly on these subjects. And that's why we went to molecular dynamics, because we wanted to go to the thermodynamics of hydrogen in situ or relevant for reservoir engineering practices and not for, let's say, chemistry or so. And this is what we are actually working on with my colleagues, Thijs Vlucht, who is a thermodynamic professor. And we are working on the equation of the state for it and all the kind of things. Because very frankly to you, I asked our chemical engineering colleagues at Delft, can you do the test for us? It's too dangerous. They said no. We don't have HSE protocol for going very, very big pressures and high temperatures, etc. But I would be delighted to speak about it with you as well. But now we are doing more molecular dynamics simulation for it.
Oh, okay, so you focus on.
Yes.
I asked you one and I just brought you the other one and then I don't anticipate you to respond. How is the efficiency on the compressible? Like because we compress this stuff and we always did methane and this stuff is pretty more compressible. I just wonder if you guys think about the efficiency once you inject the stuff like a compressor. Like, have you done any? You probably have some numbers. No, you don't.
Not
never
in my
think
mind,
about
but I can refer you to references. And this is the hydrogen economy is at the moment I'm speaking is under evolution and is scaling up. And if I would tell you about efficiency of electrolyzers today and about a year from now would be very different. This is what, because now in Europe, it's a very dynamic research topic. Yeah. Okay. But if you want to tell, if they are being considered, yes, they are. If I know it by heart.
So please email me the last one. The last one is why you care about the cyclic. What brought the, because you brought the fatigue and your cyclic load.
Yes.
What caused this cyclic load?
Because you store hydrogen in winter, in summertime when you produce a lot of energy and you don't need, the customers don't need much energy. In wintertime, you need to bring it back and supply to the grid. It's exactly like gas storage. But here you have intermittency of the renewables, at the same time intermittency of the clients. Clients use different patterns of energy, even during daily basis, and then weekly and monthly and seasonal.
Oh, so that's okay.
That's the difference.
Okay, so a quick question here online. Understanding that you're working on the lab experimentation side, but anyway, the question is for Mohammed Resk. Do you think hydrogen molecular diffusion in brine has a significant impact during hydrogen storage?
Would hydrogen dissolution into brine?
Diffusion
into brine. I don't, dissolution of hydrogen is much lower than CO2. That's one thing. Diffusion is higher, but the rate is very, very low. I would not be really worried about that.
Okay, thank you.
Compared to other concerns we have.
Good. Question on the floor here.
Yes.
That was also my question.
Oh.
I'm Saman Rezayan, a postdoc, University of Calgary, as well as visiting scholar, Hadi Hajibeygi University. I've got a couple of questions. Is DARSIM freely available?
Yes, yes. DARSIM and the DARSIM program, whatever we do at Delft, DARSIM and DARTS that Sebastian mentioned, all free, yes.
And is the PEDFM...
But we accept donations of companies as, it's not that, it wouldn't hurt us. Just.
And is PDFM included in DARSIM?
Yes, for unstructured grades, for core corner points.
I saw in one of your slides that you mentioned corner point. You developed corner point grading system in PDFM?
Yes, yes, that is
excellent.
Yes, and it's just published last year.
So back to diffusion is also my concern. Diffusion has a contribution to total flux for long-term CO2 storage. When it comes to hydrogen storage, it's cyclic and short-term. And regarding Pictet number, do we need to really include diffusion?
That's a great question. And we have numerical diffusion anyhow in our numerical practices. We have physical dispersion diffusion and we have heterogeneity. And Eric knows it much more than I would. And sometimes heterogeneity would be what you would assume that would also do the work of diffusion dispersion as well. The thing that from my perspective is important is to know the scale of real physical dispersion diffusion and know that this is the driving force for you, and not that numerical dispersion diffusion is overestimating the dilution that you think that it is being diluted there, but it's actually numerical grid block. And that's the lesson I learned with the project we had with EBN, Energy company of the Netherlands, about that specific topic for hydrogen. So we are going soon to do the test in the lab for dispersion diffusion of hydrogen. But that's if I have a few questions to ask, one of them would be this.
Thank you so much. Excellent presentation.
Thank you.
Okay, so Hadi, location. Do you have a map or have at least talk about it? Where are the best locations where you can actually store hydrogen in a substantial amount and be able to retrieve them?
It's a good CEO questions. I would say short term and long term. For short term, if you have salt deposits and you can do solution mine caverns, that seems to be the first option for you to consider.
And so where are the salt caverns?
And they are this kind of, we have in Netherlands, we have in Britain. The first salt cavern for hydrogen was mined in Teesside in UK, yes, 1972 was operational. There are 3 others for hydrogen in Texas, and the Texan ones are huge, very big. And they have been operational for decades for hydrogen, but not for cyclic hydrogen. They have been feedstock for petrochemical, for ammonia creation, etc. So if you have deposits of rock salt, that is very attractive because we know they are sealed. Others then depleted gas reservoirs would be the second option because of their scale and that we know them and we have operated them. There are some projects in Europe that they are screening the subsurface of Europe digitally to provide an open access link to potential traps in Europe continent. And there are European projects that I have seen them, etc., and discussed with them. Soon these maps will be coming out.
So have you looked at Africa, Asia, Australia?
We are waiting for the market, for the interest to come. Okay. Middle East now is becoming also Aramco. If you have talked with them, they are becoming interested. And other companies, I don't want to mention every name. Okay. But to be honest, there is yet not really much market for hydrogen. We need to understand what is it. We are working for the future to come. Yeah, but we are using our geoscience knowledge to transfer it to something extremely valuable at this time for the society. Okay, and I think that's the impact we are making.
Sounds good. So thank you, Hadi, for an excellent talk. Very informative. Thank you.